Yeah, first of all, I mentioned that I never remember where the conjugation should be. Misha corrected me. So if you have questions, feel free to ask him. I'm sorry, Misha. And we will be having a talk on harmonic embeddings, which is secretly related to all this tour, and this will be on Thursday. The fact to where to put this conjugation is obviously the fact about interchanging the roles of white and black faces. And by the way, in the current notation, so I always have an impression that we made the wrong choice in our first paper. So if you interchange the roles of black and white guys, then there will be no conjugation here. So the limits of functions that come from white faces, they satisfy this condition with theta, and okay, with one of them, and the limits of functions that come from the other color, they satisfy the condition with theta bar. So there are some conjugations put here and there, and that's just a matter of notation. There is always a sister picture. Okay, so let us continue. So let us continue there. So the first question that I wanted to discuss is what are setups in which we do have boundedness. So the first, so now we have a kind of a discrete complex analysis framework. And the first class of setups is actually more classical. This is setups like temperland domains. Just on Z2. So Z2 is a particular case. Something which might be called Ising domains or hedgehog. So in the first class, there is a link with the UST model. And K-1 in this setup are actually gradients of positive harmonic functions. So secretly, there is some positivity in the model that you can use. And positivity by Carnot principle, it actually says that we do not have these bad effects. The second class of domains, there is a bijection, okay, not a bijection, a correspondence with the Ising model. So if you have an Ising model on something like that, then what you can do, there is a bipartite graph associated with that. Which some people in the room might have seen. This is what appears, say, in Julian Dubida's paper called Bosonization procedure. And then with every Ising model, there is a bipartite dimer model associated. And the analysis of Ising observables translates into analysis of bipartite dimer observables on this graph. So this is called bosonization, combinatorial bosonization. So in both cases, there is a kind of positivity behind. So I don't want to spend time on that. So there is some positivity or Harnack for primitives or antiderivatives of K-1. Okay, and then there is another thing in which, another setup in which the positivity, in which the boundedness is known. So there is B, and that's an important new setup. So there is a theorem which is from this paper. So that's the paper on which the Lorentz perspective has been discussed. And the theorem says the following. So remember that when constructing these embeddings, when choose and gauge functions, I have a certain freedom along the boundary. So now I specify a certain assumption about the boundary under which we have K-1 bounded just all of a sudden from nowhere. So again, we observe certain hidden positivity. So the theorem is as follows. let me do not formulate another technical assumption. Like assume that our surfaces are Lipschitz, and also that a certain mild non-degenerate assumption. So this is technical. Not exponentially, non-exponential degeneracies. So assume that there is this assumption, and assume that this assumption again, for more advanced people in the room, they'll hold only on compacts. It is enough to assume the following. If the boundary of this T surface belongs to the following set, so I have a two-dimensional surface in the four-dimensional space, and I'm specifying where the boundary should be. So this is the set of all z theta such that, so I'm just, theta is the name of my second variable, such that these points belong to the light cone, and imaginary part of theta is 1. Let me try to draw a picture. So that's a very bad idea, trying to draw anything in a four-dimensional space. So this is actually a three-dimensional space because I prescribed one of the coordinates. This can be written, so that was a complex number whose imaginary part is 1. Okay, this will be hyperboloid. So this is a picture. Here there is z, which is a complex guy. And here there is a real part of theta. And imaginary part of theta is 1. Okay? So if it so happens that I have a surface whose boundary is like that, and the surface is a Lipschitz on constants, on compacts, sorry. It cannot be Lipschitz close to the boundary because these guys, they kind of go light-like. Then we know that k minus 1 WB is full 1. So those guys are known under the name perfect teammates. Now, conceptually, if we now want to analyze the limit of fluctuations in certain dimer models, then we should ask ourselves whether or not we can prove that a perfect team mating exists. Or maybe, so I was much more optimistic about this 5 years ago, or maybe invent something else. So nobody tells us that there are no other setups. A concrete graph, or sequence of graphs, if you wish, can admit many possible ways of drawings for which k minus 1 is still O1. So this is not necessarily the thing that we need to do. But that's the only non-trivial, I mean, non-standard thing that we know up to now, on which, and we do not use any assumptions about the combinatorics of the graph. So here, in that end of the story, there are very strong assumptions about what the combinatorics of our bipartite graph is. And here, there are no assumptions at all. Okay. Still, there are questions. So what we must do, we must discuss interpretation of limits here, but still there are things to do before that. And one of the things is to discuss how restrictive this assumption is. Right, so I'm assuming something a bit weird about the boundary of my graph. So first a remark, let me put it here. Those are certain algebraic conditions on the gauge. If I'm given a matrix, then this is just certain conditions about what are mismatches. I mean, how, remember that these guys, they locally belong to the kernel of K. So the only freedom that I have is what is KG evaluated at the boundary. So this is just a bunch of numbers, finitely many numbers. And this is a certain algebraic assumption about them. You can ask whether or not you have enough degrees of freedom. And the answer is that the dimension counts match. So this, the number of equations equals the number of unknown. So algebraically, you just have a system of equations of degree 4 or something like that, polynomial equations, and it sounds to be okay. However, we still do not know whether or not they're always solvable. When making any comments of that, I'm kind of putting under the rug symmetries that we have. So let me discuss symmetries because that's important. And this clarifies why, eventually clarifies why the signature 2,2 is a natural signature. Why the surfaces should be viewed as surfaces in R22 rather than in R4. So what are symmetries? Remember this definition. So I'm constantly saying that if I start with a real valued Castellane matrix, then I need to find gauge functions. Gauge functions are complex valued. So what I can do, each time I have this gauge function, I can replace it by alpha plus beta conjugate. If G was a nice Coulomb gauge, a nice solution, the function that locally belonged to the kernel of the Castellane matrix, this is still a solution. So this action is actually an action of a group U11. So this is a group that preserves this quadratic form. And you can think that you just act by these matrices on GG bar. Then that's what it is. Okay. Maybe plus scaling. Right. Here I can also multiply by real constant. So what I'm saying that if I found a nice gauge function, then I can still apply this U11, and I still have a nice gauge function. Okay. And I can do the same here. So what this means, that means that there are intrinsic symmetries in the story that tell me that there is a hidden action of the product of two copies of U11. It is that. It is isomorphic to SL2R, if you wish. Okay, that's isomorphic to two copies of SL2R. And there is also scaling, which is behind. And now there is a fact about these groups, is that if you factorize by simultaneous flip of the sign of both components, which does nothing with this choice, with this with T and O, then what you have is, I believe this is the right notation. This is the symmetries of R22, preserve orientation. Is the connected component of the identity in O22. And the statement, which you can check, that's a straightforward computation after all, is that indeed, if you do these transforms with the gauge functions, then what you do is just apply an isometry in O22. So this O22 becomes isometries of the T surface. Plainly, you just start with a gauge function. You plug in alpha beta here, gamma delta there. The results in T and O are just linear combinations of the original T and O and their conjugates, and that's a computation that the metric is preserved. So in particular, already at this point, you can just say, or I guess just from the symmetries, that this is the right perspective. Yep. So far, so good. And by the way, an important comment. It's hard to trace what's going on with T itself. If you just think that this transform is a trivial scaling of T, just a fine transform of T, it's by far no. It mixes T and O as isometries. So that's why the perspective of looking at the surfaces, T surfaces rather than T embeddings, is kind of a better one, because you immediately see the geometry. Okay, so far so good. Next comment. Next comment is what happens if it so happens that we're in a situation when the outer degree is 4. So this is a certain, we are thinking about graphs like that. So there is something, I don't remember, was it black or white? Okay, something like that. Remember the picture of the Aztec diamond. So Aztec diamond fit the thing. Anyways, yeah. I'm lost with this drawing, but you can imagine what it is. Some drawing. So in this situation, what are the dimension of spaces? So here, the only thing that we can choose is mismatches at 2 black faces. What I claim that by this action, all them are equivalent. All choices. Such that e.g. are related by this action of U11. There are 4 complex parameters here, 2 complex numbers, 4 real parameters, sorry. And this is a 3-dimensional group, and scaling does the job. So they're just all equivalent. In this case, all T surfaces are actually isometric. What I'm saying that there is no choice at all. Well, if it so happens that the outer degree is 4, then all the surfaces are isometric. And because of that, actually the notion of perfect T embeddings becomes an empty notion. Because you can embed as you wish. Now 4 points in R22, they're always by translation on a certain light cone. They're always in a hyperspace. And you can apply isometry to make this hyperspace what it is. Okay, empty is tautological. Okay, is tautological. Meaning that every embedding, in this case, every embedding is perfect up to a movement in R22. There is no free. So in this particular case, not only they exist, I mean, that's just one embedding, and it is perfect if you apply proper isometry. So in particular, if we come back to this illustration of that stack diamond, then from the current perspective, we actually have no choice at all. So what I tried to explain is that if we think about Aztec diamonds, these graphs, sequences of graphs where the outer degree is 4, then this construction is kind of canonical. We just know that such embedding exists and is unique. I mean, that's what it is. We know that k-1 is bounded. This means that because of the theorem that I formulated here, but didn't explain the proof at all, because of that, we know that there are subsequential limits because there is a regularity theory. And we should ask ourselves, okay, but how do we interpret this condition? And this is the last part of the story. I'm erasing, well, let me keep this condition and erase something else. So last part of the story. Interpretation of this condition. Okay, so ideally, we want to find conformal invariance. So we want that maybe after a change of coordinates and some transform of f, this becomes standard Cauchy-Riemann equations. This is a question from analysis because this closeness of the form, it can be written as a kind of, those are two equations on the partial derivatives of f. So this is a question from analysis whether or not it can always be brought to the canonical form, where now by canonical form, I try to think about holomorphicity. The answer to this question is negative. It's not always can be brought, and it can be written as a holomorphicity of anything. Okay, what you can always do is the following. You can say, let me define, assume for a while that theta is smooth. And I believe that in this room, I should assume that theta is smooth. So just assume it is smooth. Because I'm going to write some derivatives. I have a surface in a 4-dimensional space. Okay, that's just meaningless picture, so just some surface. However, this is a space-like surface. Remember the condition, Lipschitz condition, which was right here. It guarantees that it is space-like. In particular, it guarantees that the metric on the surface is positive definite. So I can think about uniformization. So this is my zeta. And I can uniformize it onto the unit disk. So that's just a conformal map. And I will be using this new coordinate to rewrite this stuff. So denote, again, that's a certain computation. So I'm changing z, and I'm also changing f itself. So this is z, zeta 1/2 f plus theta bar z. Well, right now, what did I say? I said that let me change the coordinate and let me change the function. So this condition can be rewritten in terms of psi and zeta. So I can try to say what kind of condition psi satisfies. Then the following holds. Ideally, I should want to have conformal invariance. But yet again, I already told you that, okay, it's not always the case. Instead, I have this equation. So this is the holomorphic derivative, Wittinger derivative in zeta, and it equals psi bar. Some f. This is a function of a point on our surface. And this is a complex valued function. For those who know a bit more about the Ising model, let me say right here that in the Ising case, M is a real function. So what I'm saying that we had a certain condition, kind of Cauchy-Riemann, and it can be always written in this form. If you wish, that's a kind of a structural theory. Now, if I want to find conformal invariance, then I should ask myself what is this M, right? Because ideally, I want to have M equals 0. And then the fact is that the absolute value of M, let me write it slightly instead of a formula, let me write just the situation when M is 0. So M is 0 if and only if this is a maximal surface. Where maximal means that the mean curvature vector vanishes. What I insist that that's a calculus. That's just computations. We already have a certain condition, and we ask ourselves about interpretations. And this is a possible interpretation. Yeah. This is not rho, this is zeta. That's my script, I'm sorry. This is like that, right? Anyways, yeah. That's a good question. So this is, give me two letters. If zeta is S plus IT, then zeta is the Z over the zeta is 1/2 the Z over the S minus I the Z over the Z. So, and the zeta bar is the same with plus, and holomorphic functions are those. Oh, sorry, yeah, sorry. Oh gosh, my gosh, this is the zeta bar. Yeah, thanks for asking. Yeah. So this is the zeta bar, and this is plus. Just blacked out. So holomorphic functions are those for which this vanishes, right? Yeah. It's very fortunate that you asked here. So holomorphic functions, there's those for which the anti-holomorphic derivative vanishes. Anti-holomorphic derivative can be written in coordinates. Okay, and what I'm saying that what we have is a more general equation of this form. Does that make sense? Okay. And now, what is the perspective? The perspective is as follows. Now, if in a certain setup we can prove that the limit of the surfaces is a maximal surface. So if in a certain setup we have perfect embeddings, we can prove that a maximal surface appears in the limit, then these techniques allow us to prove the convergence to the GFF, because we observe conformal invariance. You can ask yourself, okay, what if our surface is not maximal? If our surface is not maximal, then kind of general principles tells you that you should not see conformal invariance. And in particular, you should not see Gaussian fluctuations in the limit. That's a more advanced material, so bosonization of massive fermions is not a free Gaussian, is not a Gaussian theory. This is what is known under Sine-Gardon theory. So this creates a kind of an alternative. Either we do have, yeah? GFF for dimers, yeah. For Ising, we will have conversions to SLE, etc. Yeah. Yeah, okay, don't ask me about Ising right now. Yeah, I planned to comment on that, but there is no time at all. So maybe, yeah, maybe we will still have 10 minutes. I don't know. Yeah. So this somehow creates an alternative. So either maximal surface and Gaussian fluctuations. And moreover, in this case, what we have is, so that's the first scenario. What we have in this case is GFF in the metric of the surface in the structure, defined on this surface. Or non-maximal and non-Gaussian fluctuations. Which implicitly means that in any setup in which it is predicted that the fluctuations are Gaussian, and given that we can find perfect embeddings, the surfaces must be maximal. Importantly, we do not know how to prove this, how to prove the fact that they are maximal directly. So all the known cases in which this route is completed, they require explicit computations of k-1. And because of that, it's not terribly beneficial, because if you have a tool that allows you to explicitly compute k-1, maybe you don't need the surfaces at all, because you can just work with your computations, with your asymptotics directly. So we do have, so this alternative allows us to make a prediction, is that these maximal surfaces are inevitable in many setups. However, we do not have any intrinsic proof of that. That's where the theory is. And now we have an alternative for the remaining 15 minutes. Either I can comment a bit on the Ising model. That was my original plan, like how these notions are translated to the Ising model. Or maybe I can tell you a bit what is known in terms of concrete examples, trying to do pictures on the blackboard. That's my instant idea. I didn't prepare this at all. So myself, I would vote for Ising, but if you prefer to stay with dimers here, I would be happy. Like discuss an Aztec diamond in more details. Is there anybody following? Okay, I believe Trishen, you are the only. Pictures would be nicer. Okay, so let us try. Yeah, sure. Then please feel free to ask questions because it's going to be totally free ride.
Okay.
I'm not prepared for that.
So the question was on the non-Gaussian. You mentioned sine Gordon, but what's the parameter? Like there should be some sort of parameter for sine Gordon, right?
Right. Well, honestly, also I'm not very prepared to answer this question. If M is real, then there is what's called Coleman correspondence. Then the perimeter is obtained out of M. There are two parameters there. One should be for pi or something like that. That's where sine Gordon describes bosonization of massive fermions. And okay, M gives you the answer. Okay, if M is a complex valued function, actually I'm less familiar with this setup. However, I believe that the fluctuations are still not Gaussian in this case. Well, it's not excluded, by the way, if somebody is watching this, 2 years ago, it's not excluded that I'm saying absurd about complex valued M's. So please double check this yourself. At least for real M's, this is definitely true. Okay. So now let us try to come back to examples. That's totally a free ride. What is known? So examples, no. Most of them are, and by known, I mean explicitly computed. And basically, the primary group working on these questions is Thomas Berggren, Matteo Nicoletti, and Mariana Ruskich. Though there is a couple, or at least one other paper, but that's the primary group working on these examples. So most of them are degree 4, outer degree 4, which means that the perfectness condition is automatic. The only example of outer degree 6 is a regular hexagon. So this, you may remember this picture of the dimer model. It's a bad idea to draw triangular lattice, sorry. On the regular hexagon. Was a bad idea. Yeah, a regular hexagon that I showed in my first lecture. So in this regular hexagon, what we should observe that there is arithmetic circle phenomenon, and there are a lot of symmetries in the problem. So you can imagine that the perfect embedding in this situation exists, and it is fully symmetric, meaning that you just have this hexagon on here, got myself, hexagon on the hyperboloid, and there is a maximal surface attached to them. In this situation, by the way, there is an important thing that I want to comment. So our surfaces, they are to comment on. Our surfaces, they are surfaces in R22. However, the boundary contour belongs to a 3-dimensional space. And I claim that my surface should be maximal which means that it also belongs to a three-dimensional space. Think about soap foams. If your boundary contour is two-dimensional, then the full surface is two-dimensional. So if the boundary degenerates, I mean, dimension degenerates, then the surface also degenerates. So the limiting surface is actually in R21, which is R22 part of R22. And this is something like a monkey saddle here. There's some type of monkey saddle. This is fully computed. The complex structure of the surface describes the fluctuations. How does this picture fit here? That's an excellent question. So here, you may remember this is fully similar to what was on my slide with that stick diamond. So the whole frozen region here is mapped to a single point there. There are no fluctuations at all. The whole frozen region there is mapped to, say here, is mapped to this point, and so on and so forth. So the places in which there are no fluctuations, they collapse as they should, because I pretend that the limit is described by the GFF in the metric of the surface, in the structure of the surface. And inside, something non-trivial happens. So just check, this is similar to homogeneous. Let's take that. And this is the picture that I showed in my first lecture, and it is from here. That's our paper with Sanjay, which is 10 pages long. And the purpose of this paper is just to give an illustration of what's going on. Okay. Then you may remember there were some darts-like picture, and somebody, Luca, asked me, no, somebody asked me, not Luca. Yeah, I don't remember who. Somebody asked me, yeah, what is the meaning of blue and red colors? And who was that? Yeah, I was completely off here. It was you, no? Okay. Yeah, somebody asked me. Yeah, maybe Ulrich here. I don't remember. Yeah, I didn't sleep that night, and I'm 12 hours trapped jet lagged. So, okay, so that's what happens. Now, what about these examples? So there is already an example of an Aztec diamond, which I don't want to repeat here because we had the drawing. So importantly, what they are able to do, they are able to compute the case in which you work with Aztec, but with doubly periodic weights. So why is it of interest? And this is more going to be towards a research talk. It is of interest, yet again, so what I'm erasing the fact that there is no question of existence of perfect embeddings. This is outer degree 4, so you just take any embedding and then rotate it in R22 probably, and you, properly, and you're in the setup you're looking for. Or even you don't even need to rotate, you just compute the structure out of what it is. So from the diameter's perspective, we have this graph. This is my Aztec. And now, besides frozen regions, so this guy is frozen, this guy is frozen. There is something which is called the gaseous bubble. There. I don't have time to define what it is, but that's yet another regime of the dimer model where, so here everything is deterministic, and here it converges to the white noise. There are no long-range correlations. Again? Oh, blue is a bad choice. This saves me. No, look nice. Okay, and now there is a natural question. We do know that this perfect embedding exists. That's just any embedding. K minus 1 maybe hopefully is bounded, or okay, what happens with surfaces? How is it possible that in a certain part of our domain, there are no fluctuations? Because here, okay, there are fluctuations, but okay, it cannot be GFF. It's a different regime. So it's an interesting picture, what happens in this case. So the boundary is still the same contour. So what we have is still the same, where is yellow? It's still the same boundary contour. Something like that. And before, for the regular diamond, for the regular Aztec, what you would do, you would just attach to this contour the unique maximal surface, and this will be maximal surface in R21. So this is a picture for the regular Aztec. So this is homogeneous Aztec. Now imagine the following. So that was my rough idea of what I would present, and I'm trying to implement this plan. Imagine that you pick this point and pull your surface in the 4th dimension. Remember that that's a 4-dimensional space. Just you move it here along 4th vertex. Okay? So importantly, this doesn't break the symmetry. You could have done this already in a 3 space, but this would break the symmetry. This would be fishy, whereas the picture should be symmetric. However, you can remember that there is actually, that should be a 4-dimensional picture. And now you have a surface which is attached to this boundary contour, which is 3-dimensional, and one more point in the 4-dimensional space. There is still a maximal surface. Attach maximal surface. Surface to this boundary. And this red point. And this is what appears. In particular, the whole gaseous bubble here, the whole this region is mapped to this point. So as before, these frozen regions are mapped to these 4 corners, and the gaseous bubble is mapped to these 4. So on the technical side, this surface is not K-Lipschitz right near this point. So what happens there, you kind of, when you pull it there, the maximal surface approaches the light cone. However, the complex structure is correct, and you can just compute it and confirm it. So to this setup, the theorem of this paper does not apply directly, because to claim that K minus 1 is bounded, in that paper, we needed to know that the surface is Lipschitz everywhere inside. So this is a more interesting doubly connected setup. And this is, well, I hope that I'll be working on this. So I was in limbo for quite a few years, but now, there is some progress, notably here. Okay, I hope that we'll be developing this further. However, that's what I wanted to show is that there is actually a quite interesting geometry. Of course, this was conjectured already in our first paper, that there should be cusps like that. And of course, the general conjecture is that if you have more gaseous bubbles, then you simply put more points here and there and attach a maximal surface to a number of points and a certain one more example. Here I should stop, but one more example is that there are setups in which the picture looks something like that. I will not be drawing the full picture, but this arctic curve, it may behave something like that. And then there are regions which are called semi-frozen, but anyway, there are no fluctuations there. So that they are still along the one side of our domain. So this is still outer degree 4 case. And you can ask what happens with these semi-frozen regions here, because we have only 4 corners. This is still outer degree 4. So even though here there can be many more frozen regions, there is a kind of mismatch of the count. So in this case, they checked that part of them is collapsed to one end and another part is collapsed to the other end. So this still works as it should. And to the best of my understanding, so I cannot tell for them, but to the best of my understanding, they are working on understanding more examples and trying to give a more consistent glossary of what is expected. I believe that's a good point to stop. I didn't have time to speak about Ising, but that's life. Questions?
Testing. Okay. So of course, Ising and Dimer, so in the space of planar models with height functions, I guess Ising and Dimer are very special in the sense that you can sort of just cook up your S holomorphic observable. Nonetheless, do you have any hope that other height function models admit such a surface picture, such that you say anything that's supposed to converge to GFF sort of has this maximal surface picture? So
personally, I do not. So personally, I've been criticized for that heavily. However, I myself make a very clear distinction between the two cases. The free fermion models, when you do have determinantal formula, fortunately still here, or Pfeffian formula, so for Ising, that's a Pfeffian of something, and you immediately have fermionic observables. Because instead of defining them in whatever way through paths, they came up from just saying, let us think about k-1. If you read the seminal paper by Stas of 2006, his talk on ICM, not the Fields medal, but the first one, it's explicitly mentioned there that, okay, they appeared in the Ising case as dimer observables. And then he cleverly generalized them for other models, and this is what was crucial for the whole progress. However, they appeared first in the Ising case. So my perspective is that this only applies when you are at a free fermion point, which is unfortunate, but that's what it is. I'm sorry for that, but yeah, I want to be clear. That's a very good question, and I want to be clear on that. Still, you can hope that maybe, I don't know, maybe, I know that some people in Geneva tried. Maybe you can try to play with other models on this type of tilings and try to find some weights for which there is a partial information, like there is still like half of relations or something like that. For me, yeah, I don't know. I would be surprised, but yeah, who am I? Yeah, I would be surprised. For me, that's very specific.
so here. Maybe what's not clear to me is how, I mean, yeah, that's like white noise.
Again?
So what I'm unclear about is how you can. Yeah, what I'm unclear about is how you can guess the type of fluctuations from where you are on the surface. So maybe the points being frozen, that's fair, but there's the fact that that you have a red point and somehow it should correspond to something where you have white noise fluctuation. So is there any sort of like heuristic for this?
Yeah,
or?
okay, yeah, that's exactly, yeah, yeah, so thank you. Yeah, now I have a chance to repeat what I said very, very quickly. So there is a setup in which this bubble appears and your steel is very symmetric. So this is related, this is massive dimers, if you know what it is, what they are. So you just have a square grid and you have two weights, one for that, not necessarily massive, sorry, and one for that, and that's it. So there are just two weights. And you can draw an Aztec diamond on top of that so that you are fully symmetric. Then you kind of expect that there should be a symmetric picture in the right hand side, on the right-hand side. This is, by the way, not fully trivial because there are examples in which you start with symmetric graphs and then you observe that they admit perfect embeddings, but those are not symmetric. So there is a symmetric break-in effect. So that's the question about the existence of them is really not that innocent as it looks. And that's why I'm now a bit more pessimistic. However, if you hope for good, like I'm drawing you this example, and then you go down the same way. So it is fully symmetric, and you can hope to see a symmetric picture. There is no flexibility in choosing the boundary contour because they are all by isometries equivalent to each other. So you start thinking about, okay, what can I do? Something should appear at the center. And you start thinking, okay, what can I do? I cannot move it to the right, left, because I break the symmetry. I also cannot move it up in the same space because I break the symmetry with respect to this direction. And you feel stuck for a while, but then you remember, but no, we should be in R22. And there is this position of this red point, which keeps the symmetries of the original guy. And this is what leads you to the guess. And then it is confirmed that in this situation, this is exactly what happens. So how far you go depends on what is the ratio of the two. I hope that I'm saying the correct thing. At least that's the natural guess. And then you can ask yourself what happens in the limit when the ratio tends to infinity. And this point goes maximally far so that the surface is still 1 Lipschitz. It becomes a degenerate surface, actually. This is just, this will be T coordinate and this will be O coordinate, but already in the limit. So this will be a red point here, which traveled all the way, as far as possible in the first direction. So that's the heuristics. That's a great question. I hope this helps at least a bit. No, it was like an algorithm starts speaking something and then wait for a couple of seconds because it recognizes that. Oh, no, it's.
I was curious about double dimer model, and so in that case, SLE4 appears.
That's a long story. Prediction is that you should see CLE4 loop ensemble, say in this simple example in this metric. We are quite far from proving that. The best result towards convergence is in temperland domains. This is our joint paper with Misha, which is based upon Julien Zubedaz and Rick Kenyon's work. What we can do in temperland domains, we can show, I'm sorry, it's long. I mean, like, for any number of punctures, if you only keep the loops that surround at least 2 punctures and ask what is the probability to see this or that topological type of configurations for double dimers, then it converges to the same for CL4. So we are, then this is up to you to decide whether or not you are satisfied with this topology. It gives you a lot of information, like it distinguishes, for instance, this loop from that loop. And then the state of the art is that people do not know precompactness statements for double dimers. All of a sudden, this is totally opposite to what happens in percolation models. In percolation, in FK, and things like that. There you have crossings, etc. You have precompactness, and then the problem is in proving the convergence. And here there is no precompactness. But if there was precompactness, it would be convergence. This is in temperland setup. Generalizing this even to Aztec with homogeneous weights is not simple. It's not a simple question. So I believe we now have enough tools for that, but this is a big work to be done. So in particular, I cannot claim that I'm fully certain that I can write it in, I don't know, half a year. So there might be some pitfalls. I don't know. So that's a kind of, that's an important question. So maybe that's something that one should do.
Thank you.
Hi, is there some characterization of when the limiting surface will be in R21 and not R22? Or is it just not relevant?
No. What I want to emphasize that the only non-trivial case that we know is this perfect embeddings. We insist that the boundary is in a 3-dimensional space. Because of that, if the surface is maximal everywhere inside, then it is automatically in the 3-dimensional space. So the only thing that can kick it out of this hyperspace is possible gaseous bubbles inside. And then, well, no, there are other examples. If you shift this picture somehow, then this breaks the symmetry and this guy goes up in the same hyperspace. So I don't think there is a meaningful characterization here. So that's a good question here, but I don't think there is a concise answer to that. So just check examples. I think that checking examples from this paper would be a good idea. That's not the only one. What I did here is not the only example that they have. So check the work of this group.